The first step in physics is Newton's laws of motion. But let's be honest, do you really know the story behind each law? How were they discovered? How did they even come to exist? After this video, some of you might walk away thinking they weren't even Newtons. Hey everyone, welcome to Cosmic Colors. In this video, we are going to uncover the real colors of Newton's laws of motion. Before we dive into the laws of motion, you need to understand a few basic concepts: inertia and momentum. And believe me, these are crucial to understanding Newton's laws. About 50 years before Newton, Galileo wrote something powerful in his book. Here's a translated version of what he wrote. In easy words, inertia is a property possessed by every object in this universe. It helps the object stay in whatever state it's already in, either rest or motion, and it resists change. And now you are ready to go deeper. Inertia explains why object resists change. But to understand how motion continues, you need to know momentum. Momentum is a conserved quantity in a closed system. It can't be created or destroyed, only transferred. So if there is no friction or external force, an object stays in its state because constant things don't change automatically. That's why in deep space, a spacecraft can glide for thousands of years, no engine needed. Now imagine you are in space and you throw a ball. Let's call it ball X with mass m. After traveling a while, it hits another ball Y, which has the same mass. Because of the collision and equal mass, ball Y starts moving with the same speed and direction, and ball X comes to stop. That's momentum conservation in action. The total momentum of the system stays the same, just shared between the two objects. This happens everywhere. Bat hits the balls, even molecules bouncing in the air. But what if we actually want to change the motion of something? To do that, we need to change its momentum over time. And that's Newton called force. So when we change momentum with respect to time, we get F equals to ma. It may look simple, but that's what makes Newton a genius. It's simple, powerful, and it describes how everything moves, from rockets in space to falling apple. That's a lot, but now you are ready. You can finally understand Newton's laws, not just as rule. Newton's first law of motion says, an object at rest stays at rest, and an object in motion stays in motion at a constant velocity unless acted upon by a net external force. Just a few minutes ago, we talked about inertia, and this law is where it becomes real. Inertia has a tendency to resist change. Newton added this: change only happens if a force steps in. That's the beauty of the first law. It tells us something subtle but powerful. In this universe, nothing changes unless something makes it. If the first law tells us when motion changes, second law tells us how much it changes. Newton's second law of motion says the force acting on an object is equal to the rate of change of its momentum. In its most famous form, F equal to ma. It means the more mass something has, or the faster you want to it accelerate, the more force you need. This is why it's harder to push a car than a bicycle, and why fast sport cars need engines that generate massive thrust. But here's where it gets interesting. Force isn't just a push or pull. It's the cause behind acceleration. It's what bends the motion. It doesn't just describe motion, it lets us shape it. It's the bridge between what we want to happen and what actually happens, and that's why Newton's second law became the backbone of engineering, rockets, machines, and many more things. Now we arrive at Newton's third and final law, probably the most quoted law in all of physics. For every action, there is equal and opposite reaction. At first it sounds poetic, but just a moment ago, we learned that momentum is always conserved. It never vanishes, it just shifts. Now, here's the connection. Newton's third law is how that shift happens. When two objects interact, they apply equal and opposite forces. Not just forces, but equal and opposite changes in momentum. If one gains momentum, the other loses it. Perfectly balanced. Kick a soccer ball and your foot jolts back. Every reaction you feel is the universe protecting momentum, keeping the total motion in balance. It doesn't just describe forces, it reveals how the universe enforces symmetry. I know it's been a while since my last upload, but I'm back now and I'm not planning to disappear again. So hit the subscribe button if you like this video. Thanks for watching.